Okay, so welcome to this lesson on electrical power. Please date your work as regular so we know when you did your work. Really, we're just going to introduce a new formula today, and it's how to calculate power. Now, we've already come across the term power, so if you need to go back and have a look at what we've done there before. That was in the electricity, in energy one. Power is energy transferred or work done divided by time. You could rearrange that to say energy is equal to power times time. If you remember, power is the rate, how much work or how much energy you get through in a certain amount of time. So what I'd like you to do is try and do these two starters that you'll see on your sheet. Starter 1 about a bulb using 7.2 kilojoules of energy, and starter 2. Okay, so let's go. So the important thing here is always give yourself time to try and do the solution yourself. And then this is what I'm showing you how to do it so that you know how to do it. So please, if you haven't got the correct answer, please correct your work at the end. So these are going to use all of these. These two are going to use power equals energy over time, or energy equals power times time. Show that it's power. So power is energy over time. So the bulb uses 7,200 joules, that's 7.2 kilojoules, divided by in 2 minutes. 2 minutes is 2 times 60, so that's 120. 2 times 60, because it's 2 minutes. So 7,200 divided by 120 equals 60. And the units 60 watts, which equals 60 joules per second. Okay, that's the first one. A 2 kilowatt motor is on for 10 minutes. How much energy does it use? Choose from 20 joules, 20,000 joules, 1,200 kilojoules, or 5 joules. How much energy? Well, the formula is power equals energy over time, or energy equals power times time. In this case, we're going to use energy. So we've got 2 kilowatts and 10 minutes. So it's a 2 kilowatt motor. So that's 2,000 watts times time, 10 minutes, 10 times 60. 2,000 times 10 times 60. That's 1,000. That's 120,000 joules, which is 1,200 kilojoules or 1.2 megajoules, whichever one you want. So that was my answer. Just a reminder of where we are in the syllabus at the moment. We're working through electricity 2. We've done about AC, DC, we've done about plugs and wires and the earthing, and now we're coming back to a couple of formula-based lessons using formulas for calculating power and energy in electricity. So here is the formula that we're going to go through today. Well, fundamentally the formula we're looking at is power equals current times potential difference, or voltage. Power, remember that one? Power is joules per second or measured in watts. They are the same. Current, I've just got here amps, but it's also coulombs per second. Never get tired of saying that. And V, the best word for potential difference for V is potential difference, and that's measured in volts. So if we cover up, let's get something to cover up with. Let's see, let's make a little box here. Right, oh, there we go. Let's cover up P. And what do we see? I times V. P is I times V. Let's cover up I. What do we see? I is P over V. I is P over V. And the last one, we cover up V. What do we see? V is P over I. If you've got your own way of doing that and you prefer your own way, then just leave it at that, it's fine. What is this then? What do you think these words say down here? Pause if you're not sure. Okay, here they are. It's the same power as from the energy unit. It's just a different way to calculate it. So when we were looking at the energy unit, we said power equals energy over time, or energy equals power times, and that's just exactly the same. Okay. Calculate the electrical power supplied to each of the following. So, in every single case here, the formula is going to be P equals IV. Now, in this lesson, we don't really need to worry too much about which formula to use, but really this is the skill that we're developing when we're doing physics. In this lesson, the lesson is about P equals IV, so it's really important in every single question, just write out which formula you're going to use to solve. So, a 230 volt electric motor when the current is, so we're trying to find power, and we've got V and I. So the obvious formula is P equals I times V. I is 2 times 230, which is 460 watts. Even I'm going to get bored of watching writing 460 joules per second every time, but 460 watts is 460 joules per second. Next one, a torch lamp that has a current of 0.5 amps passing through it when the potential difference across it is 3 volts. P equals I times V. 0.5 times 3. You do that one in your head. Half of 3 is 1.5. Half of 1.5 is 0.75. So 0.75 watts. A 12 volt lamp that has a current of 3 amps passing through it. P equals I V. 3 times 12. 36 watts. A resistor that has a current of 0.0 amps passing through it when the potential difference is 6 volts. P equals IV. 0.2 times 6.0. 0.2 times 6 equals 1.2 watts. Okay, calculate the current flowing in a rheostat. This is a rheostat, it's a type of variable resistor. If the electrical energy dissipated is generating 34 watts of heating in the coils of wire that make up the rheostat. The PD across the rheostat is 12 volts. So you can see I've got that's power and that's voltage, potential difference. So we're going to start off with P equals IV. But in this question we've been asked to calculate calculate the current. So I equals P over V. P is 34, V is 12, which equals 34 divided by 12, 2.83. 2.83 amps, coulombs per second. Okay. A 2.4 kilowatt electric heater is connected to the mains 230 volts. What is the current in the heater when the heater is working at full power? Okay, P equals IV. So the only thing they really tried to make that a little bit tricky is change that to 2.4 kilo. So it's going to be same as above. I equals P over V, which equals P is 2,400 divided by 230. 2,400 divided by 30, which 2,400 divided by 230. 10.4. 10.4 amps. What size fuse would you use for this heater if you had to choose? Right. Well, what would happen to a 1 amp fuse? 1 amp would blow because it doesn't. 1 amp doesn't support 10.4 amps. A 5 amp would blow. So the only option here will be a 13 amp fuse would be appropriate in this situation. Well, we can also combine the power equation that we've got here with Ohm's law. So let's see how that would work. P equals IV is the formula we've done today, but V equals IR is Ohm's law. If we take this V here and replace it with IR, what do we end up with? Well, so that's your P equals I times V. But we just replace V with IR. We rewrite that like that. We end up with P equals I squared R. That's another formula you need to know. It's really another way of getting to the same root. You won't get different answers if you calculate using the power either way. So P I squared and R is our triangle here. So everything means the same. P is still power, still measured in watts. I is still current, still measured in amps. R is still resistance, still measured in ohms. So we know that P equals I squared R. If we cover R, we know that R equals P over I squared. Slightly more tricky one. I squared equals P over R. I squared equals P over R. So I equals the square root of P over R. So remember, in the exam, you will need to remember this formula. I would suggest you remember this one, P equals I squared R, and remember how to go through this process. And there's your complete. That's what your booklet should look like. So these formulas use a slightly different formula for power, which is the power current and resistance. And the three formulas we get from here are P equals I squared R, R equals P over I squared, and I squared equals P over R. And that tells us that I, we do this in 2 stages, it's easy. I equals P square root of P over R altogether. So I've drawn those at the side. Calculate the power that is transferred to a 56 ohm resistor that has a current of 1.2 amps in it. So I'm asked to calculate power, and I'm going to be given resistance and current. So the obvious one is P equals I squared R. 1.2 squared times 56. 1.2 squared times 56. 80.6. Just to fix. 80.6 watts. So that just means joules per second again. It's just a different way of getting there. It's just a different way, so it's the same. It still means power exactly the same. Number 2, calculate the resistance of a filament bulb that is producing 100 watts of light and heat energy when it has 0.3 amps flowing through it. So we have to calculate resistance R, and we're being given P and I. So we're still going to use it's an IP and R formula. So P equals I squared R, but R is P P over I squared. Let's put the P in. P is the power, 100 watts. And 0.43, don't forget the square, 0.43 squared. Let's do that on the calculator. 100 divided by 0.43 squared. 541. 541 ohms. 541 ohms. Great. A current flows in a wire and generates heating that produces 5 watts per meter. There's my power, 5 watts. The resistance of a meter of wire is 0.4 ohms. And what is the current? Okay, so we've got resistance. Even though it's resistance per meter, but we're working in, we've got power, watts per meter. So what is the current in the wire? Let's see, I've got P equals I squared R. That's still the same. But this time we're trying to do I. Now I'm just going to lay it out here again. So that says I squared equals P over R. If I squared equals P over R, then I equals the square root P over R. Because if we square that side, we must square the other side. So that's that same formula again. What is the square root of P over R? Well, it's the square root of P, which is 5, divided by 0.04. Let's do it in 2 stages to make it simple. 5 divided by 0.04 equals 125. And the square root of 125 is 11.2 to 3 sig figs. 11.2 watts. No, we weren't calculating. No, we were calculating amps, weren't we? We were calculating amps. We were calculating I. Okay, thank you. Okay. Let's start. A current of 0.5 amps is passed through a 100 ohm resistor. There's resistant, I. Calculate the potential difference. Okay, so they're taking me down the route to find V. I need a formula of V, I, and R. That's Ohm's law. V equals IR. Nothing to do with power so far. So 0.25 times 100. Even I can do that in my head. That's 25 volts. The electrical power supplied to the resistor. Well, I've got V. I've got V. I've got I. I've got R. So I'll do it 2 ways. The first way I'm going to do it is P equals IV. P equals IV. I is 0.25 and V is 25. 0.25 times 25 equals 6.25 watts. What would have happened if I'd used P equals I squared R? P equals I squared R. 0.25 squared times resistance 100. Let's see. 0.25 squared times 100 equals 6.25 watts. Clearly the same answer because we're calculating the same thing. 2. The electrical energy supplied to a resistor in 60 seconds. Well, if we know power equals energy over time, then we know energy equals power times time. Well, we've got our power up above. So power is 6.25 watts or joules per second times 60 seconds. 6.25 times 60 equals 375. 375 joules. Calculate the current through a 230 volt 100 watt electric heater when it operates normally. Well, the formulas I've got available to me are P equals IV and P equals I squared R. Well, I've been given V and I've been given P and I've been asked to calculate I. So I'm going to go with this one. P equals IV. If you need to do the triangle, that's fine. Do the triangle. P, I, V. I equals P over V. Power, 1000 divided by 230. 1000 divided by 230 equals 4.35. 4.35 to 3 sig figs amps. State and explain which fuse, a 4 amp, a 5 amp, or a 13 amp fuse. Well, this heater needs 4.35 amps to work. So if I put a 3 amp fuse in, a 3 amp fuse would blow, break, melt, because the 3 amp fuses aren't designed. 5 amp fuse would be good, because that should take 13 amp fuse, well, that would work, but if my device wasn't working properly, if something got jammed in it, and then it was trying to take too much current and started overheating perhaps, then the fuse would not blow. And that's the idea with fuse. You want it to blow when your piece of equipment is not working appropriately, i.e. when it's taking too much current. But fuse won't break until 13 amps. So the correct answer was the 5 amp fuse. A main circuit lighting has 4 230 volt 100 watt lamps connected in parallel to each other as shown below. The circuit is connected by a fuse. There's my fuse, there's my 4 bulbs. Now all of these bulbs are connected in parallel, so they all get 230, so let's take our time, 230 volts. We'll have current coming down here, and we'll have current flowing back out there, and that current will be the same. So I've got V and I've got P. So let's do the same as before. It's P equals IV, and I'm going to put I bulb equals V over P over V. Power is 100 and the voltage is 230. 100 divided by 230 equals 0.435 amps. And so you might think, well, I'll be okay, so that's my answer here. That is actually my answer, 0.435 amps. State and explain which fuse, 1 amp, a 2 amp, or a 3 amp fuse you should use in this circuit. Well, you might initially just think, well, I've only got 0.43 amps. But if I look carefully, I've got 0.435 0.435 amps here, another 0.435 amps here, another 0.435 amps here, and another 0.435 amps here. So my current in this main circuit is going to be 4 times that. So right, 0.435 times 4 equals 4 times I bulb is equal to the I in the current in the circuit, which is 1.74 amps, because the circuit in here where the fuse is providing 4 bulbs. Therefore, use the lowest possible bulb, the lowest possible fuse for which would make it work, and that would be using a 2 amp fuse. That would be the best choice there. Let's have another look. A 50 ohm resistor in a circuit has a current of 0.2 amps passing through it. There's my resistance, and there's my current. The charge passing through, so that's time. Well, that's taking us back now to another totally earlier formula. I think this one, so this is, we've been asked to find Q, and we've got I, T, and R. The formula that springs to mind for me is Q equals I, T. We've got 0.20 times T, 20, 0.2 times 20 is 4 coulombs, because we've got 0.2 coulombs per second. That's what an amp is, times 24 coulombs. The potential difference. So now we've been asked to calculate V. What have we got? Any formulas coming to mind here? I can think of one. Ohm's law. Ohm's law. What's Ohm's law? V equals I R. I is 0.2 and the resistor is a 50 ohm resistor. 0.2 times 50 is 0.2 times 50 is 10 ohms. How much electrical energy? How much electrical? Well, we know electrical energy. This is going to be a power question. Energy equals power times time. But we don't have power. There's no. But we do know how to calculate power from the information we got. We know that power equals IV. So I can just rewrite this times I times V times T. That's just the same as above. Sometimes in other syllabus they actually ask you to learn this. IVT. Energy is IVT, and that's really just saying energy is power times time. This is energy is electrical power times time. Let's put the numbers in. 0.2 times 10. Oh, I just spotted a mistake. 10 volts. 0.2 times 10 times 20. 0.2 times 10 times 20, which is 40 joules. Very good. A 12-volt battery is connected to a lamp in series with a resistor and an ammeter. A voltmeter is connected across the lamp as shown below. The ammeter reading is 2.5 amps. And the voltmeter reading is 9 volts. Calculate the charge passing through the battery in 20 seconds. There's only one formula really with charge and timing, and that's Q equals I T. 2.5 coulombs per second, 2.5 amps equals or means coulombs per second. So in 20 seconds we would get 2.5 times 20. 2.5 times 10 is 25, so that's 50 coulombs. What's the electrical energy supplied? Well, this is going to be E equals power times time. But remember, power is current times voltage times time. What's the current? 2.5 times. Now this is the battery here. This may be tricky. It's the battery. Electrical energy supplied by the battery. The battery has got 12 volts across it, so it's not this 9 here. The battery is actually providing energy to the resistor and the bulb. So it does ask in the question about the battery. 2.5 times 12 times 20. 2.5 times 12 times 20. 600 joules. Show that 450 joules of electrical energy is supplied to the lamp in 20 seconds. Well, here's the lamp. This is going to be the same as above, really. Let's just do it a little bit quicker. E equals P times T, which equals I times V times T, which equals 2.5 times, but this is the electrical energy going to the bulb. So that's only taking 9 volts times T. This is a question tells us that actually comes out at 450 joules. Calculate the electrical energy supplied to the resistor in 20 seconds. Well, cell provides 600 joules and 450 goes to bulb. The only thing to take the energy left is, we can say the resistor must get 150. It's got to be the difference because the cell is providing energy to here and there. Another way to if you wanted to see it mathematically, what must this voltage be? This is 3 volts. But it's got 2.5 amps. The whole of this circuit has 2.5 amps. Everywhere in the circuit has 2.5 amps. So let's see. P equals IV T, which is 2.5 times 3 times 20, which is 150 joules. No surprise there. Okay.